The next reaction is called halogenation. So we are adding X2, or basically two halogens across the double bond. Now the halogens that we are going to use are Br2 and Cl2. We are not going to use fluorine and iodine because fluorine is too reactive and it's not safe to work with, and also iodine is not giving a good yield. So now about the stereochemistry of this reaction. So halogenation occurs with anti-addition. So for example, if you want to add Br2 across this double bond, if one of the bromines is in wedge, the other one is added in the dash. And of course, we are going to draw its enantiomer as well because we are forming two chirality centers. Now, we are going to discuss why addition in halogenation is in anti-fashion. Before I talk about the reasoning for anti-addition in halogenation, I would like to discuss the mechanism here. So the double bond is a source of electron here. Therefore, the double bond will act as a nucleophile, and bromine is actually our electrophile. So we know that bromine is electronegative, and also if I draw the Lewis structure for the bromine molecule, it is completely nonpolar. So how is it possible that bromine molecule acts as an electrophile? So if we place the bromine next to the nucleophile, such as pi bond, we'll see that it's polarizable, meaning that it can form a temporary dipole. So if we put some sort of nucleophile which is negatively charged next to the bromine molecule, the positive charges on bromine will move to the side closer to the nucleophile, and all the negative charges will go to the opposite side, which is basically far from the nucleophile. Therefore, this bromine will act as an electrophile, and this one will act as a leaving group. So in the first step of this mechanism, pi bond attacks the bromine, which has partial positive charge, and the next bromine leaves the molecule. Now let's look at the mechanism for the reaction that we just discussed in the previous slide. So in the first step of this mechanism, we have the alkene, so the alkene will act as a nucleophile, attacks the positively charged bromine, and we are going to get rid of the next bromine as a leaving group. Then one of the lone pairs on the bromine will also attack one of the carbons across the double bond to form this bridged intermediate. So I'm going to show the stereochemistry here. That stereochemistry can also be in dash. So we are going to form the bromonium ion. This is the intermediate, the bridge intermediate. So this intermediate is very unstable, and this is the mechanism that is shown in your book. However, there are some cases that this step is shown differently, and I'm going to show that to you. So if the pi bond attacks this bromine, and basically the second bromine leaves the molecule, we are going to add bromine to one of the carbons. Therefore, the other carbon would get the positive charge. So we are going to form this molecule. And this one gets the positive charge. Now, to stabilize the positive charge, what will happen is that bromine will come closer to the positive charge, and basically coordinates to the positive charge. So therefore bromine will take some of the positive charge to stabilize the charge. So this bond is not actually a bond, it's a coordination. However, in your textbook it is shown in this way. So for the sake of mechanism and to follow your textbook, we are going to show the bromonium ion as it is shown here. But actually the bromonium ion is this molecule, and this is not a real bond. It is just showing the coordination of the bromine to the carbocation. Now, after forming the bromonium ion, we still have the bromine that left the molecule, which is negatively charged. So this bromine will act as a nucleophile and attack one of the carbons and opens up the bond. So we are gonna form this molecule. So after opening the bond, this bromine, the stereochemistry here does not change. It is still in wedge. However, the nucleophile attacks from the basically bottom, so we need to show that in dash. Now the bromine can also attack the top carbon, and that forms the enantiomer. So this is the reason that we have anti-addition in halogenation, because the second bromine, the nucleophile, attacks the molecule from the opposite side. So we are going to add two bromines across the double bond in opposite directions. A similar process to halogenation is halohydrin formation, where we are adding a halogen and OH across the double bond. And in order to perform such a process, we need to do halogenation in water. So if you look at this example, we can use bromine or chlorine, and of course water as a solvent, so we can form halohydrin product. And specifically here we call this molecule bromohydrin, and we are also making its enantiomer. So we are forming two chirality centers. We need to show the stereochemistry. Now let's look at the mechanism here. So in the first step of this mechanism, which is completely similar to halogenation, pi bond attacks the bromine and kicks off the second bromine, and also lone pair on bromine attacks one of the carbons across the double bond to form bromonium ion. Okay, so bromonium ion is very unstable. Then water will act as a nucleophile and attack carbon, open the bond to form this product. So again, after opening the bond, the stereochemistry here does not change. However, Water is a nucleophile, attacks from the bottom, so we need to show dash bond. Now to form the desired product, another molecule of water will act as a base and takes the proton to form the product. So, and we are gonna form its enantiomer as well. Now in the first step of this mechanism, bromine negative left the molecule. Now the question here is that why water acts as a nucleophile but not the bromine negative? We know that bromide is the better nucleophile comparing to water, so why water attacking the bromonium ion? So what's happening here is that we are in the solution of water. So we have millions of water molecules comparing to the small number of bromine negative that can form in the first step of the reaction. So the chance of water approaching the bromonium ion is way higher. Therefore, water will act as a nucleophile to form the halohydrin product. Now let's look at the stereochemistry of halohydrin formation. So if we have unsymmetrical alkene, halogen will be added to the less substituted carbon and OH will be added to the more substituted carbon. And the reason behind that is because water attacking the more substituted carbon faster than the less substituted one. So if you are forming a chirality centers, don't forget to show the stereochemistry as well. So for example, so we have this alkene that reacts with bromine and water. So we have unsymmetrical alkene, bromine will be added to the less substituted carbon and OH will be added to the more substituted one. So we are going to form this product. Now we know that addition is anti, so I need to show wedges and dashes. Now since we are forming two chirality centers, we need to show its enantiomer as well. So we are going to form two products here, a mixture of enantiomers. Now let's look at halogenation of alkynes. So again, we are adding X2 or two halogens across the pi bond. Now here, because alkyne have two pi bonds, we can add one equivalent or excess amount of halogen. And with either of them, we are going to get different products. So if we add one equivalent of halogen, let's look at this example. With one equivalent of halogens such as chlorine, so it's unnecessary to write one equivalent in the parentheses. I just write that for clarification. If you just see one chlorine written on the arrow, we assume that it is one equivalent. If we have more than one equivalent, it should be mentioned on the arrow, such as writing excess. Also, the solvent for this reaction will be CCl4, which is carbon tetrachloride, and sometimes you may see CHCl3, which is chloroform. But carbon tetrachloride is more common. So with one equivalent of chlorine in carbon tetrachloride as a solvent, we are going to form both trans and cis isomers. So this is the cis, this one is the trans, and we know that trans is more stable, so it is going to be our major product. So the mechanism for alkyne halogenation is not fully understood, meaning that if the halogenation want to happen similar to alkene, only the anti-product should be produced, which should be the trans product. However, we are forming both cis and trans product, so the mechanism is not known completely. Now, if we have excess reagent, for example, reagents such as bromine in excess, so we are adding bromine across the triple bond twice, and we are gonna form this product. So be aware that the solvent doesn't change. We are still using carbon tetrachloride. It's just a solvent, so don't think that we are adding chlorine and bromine to double bond. It is completely incorrect. And also we are not forming a chirality center here, therefore there is no need to show the stereochemistry